Hello, I'm Michal and I'm going to explain the solution to problem H. In this problem, we have a score that starts at 0, and there are 10 possible ways to score an integer number of points. All of these ways give you additional points that are between 1 and 1,000, so we can think of these ways as some coins that have values between 1 and 1,000, and we are using these coins to create bigger and bigger sums, and the sums that we can create are kept at the limit m, that is up to 10 to the 18. And so the first question we may ask is like, what are and what are not reachable sums in this range? But we are interested in one specific property of those. We are using boards with individual letters to display those scores, and we need to purchase a sufficient number of each digit. So for each value of a digit, so for each 0, for each 1, and so on, we will be asking the question, what is the actual maximal number of boards we can get? Minimal number of boards that is sufficient to display any of these valid reachable score combinations. And there is one additional trick to this problem that is making the implementation slightly nastier, which is that in this problem, the numbers 6 and 9, those two digits are interchangeable because you can use the same board and just turn it upside down. So when we are counting 6s, we are actually counting the most occurrences of 6s or 9s within the same number. So how do we approach a problem like this one? The main idea is to think about the reachable sums, and there is a well-known property like when you have two different numbers a and b that are relatively prime, then you will be eventually able to construct all values that are sufficiently large. In particular, everything bigger than a times b can be constructed. This is sometimes called the Frobenius coin problem or the chicken McNugget problem. And for two values, we know the exact upper bound, but we can generalize the upper bound at least very easily to arbitrarily many numbers, because like now when we realize that for relatively prime numbers, you can eventually build all possible sums, then if the two numbers instead have a common divisor d, then you can build all multiples of d, and obviously nothing else, because anything you build as a linear combination of those two coins will be divisible by d. And now you can, by induction, add new coins one at a time and reiterate the argument that there will always be an upper bound that is such that from this upper bound, if the set of coins you have has a GTD of 1, then everything bigger than the upper bound can be reached as sum of the non-negative linear combinations. And this then again generalizes to if the GCD of the coins you have is d, then all multiples of d beyond some upper bound are reachable. And we can actually prove that this upper bound is roughly quadratic in the size of coins. It cannot be small, it cannot be bigger, because if you consider a graph where the vertices are remainders modulo the value of one of those coins, and you can then build directed edges that start from 0, and from each vertex and for each of the other coins you have an edge that corresponds to adding one more piece of that particular coin, then the reachability in this graph tells you how to reach each of the possible remainders modulo the value of the chosen one of the coins. In this graph, we have already proved that all of the vertices are reachable. And if you look at the shortest path to reach such a vertex, then the shortest path will use at most as many, well, it will not visit the same vertex twice, and this can give you the upper bound that, like the square of any coin sizes, should be the limit. So what this tells us is that so as the coin sizes in our problem are roughly 1,000, this means that beyond a million, all of the reachable sums will be regular, and this gives us one way to solve the problem, which is to do a knapsack style DP for values up to a million or maybe up to a few million, just to be sure that we are not having any problems with rounding. And for all of those numbers, for all those sums that are reachable, we actually brute force, look at all of their digits, and pick those as potential solutions. And for all of the bigger numbers, one possibility how to solve the rest of the problem then is to do digit-based dynamic programming. So we can, for instance, try to construct the bigger numbers by first choosing the length of the number, and then as we are building the number from the left to the right by adding one digit at a time, we need to remember what is the number of digits we still have to place. We need to remember whether we are already sure or not that we are smaller than the upper bound that we have. And we also need to remember two other things. One of them is how many digits of the type that we are counting we already used. So we will be running this separately for each digit. So for instance, for 8s, as we are building the number one digit at a time, we are keeping track of how many 8s we already assigned to the digits we already processed. And the last bit we are keeping track of is the remainder our current prefix gives modulo the GCD of the sizes of our coins. And we want to construct at the end a number that will be divisible, and any such number is actually reachable if it's long enough, and out of those we then pick the one that had the most digits that we are interested in. So knapsack for small values, digit-based DP for large values gives you one correct complete solution. And there are also other things here that you can do. For instance, you can realize that if the upper bound has d digits, then there will always be a solution with, for any specific digit, there has to be a number that is reachable, and almost all of the digits are of that type. So for instance, if you want to count what is the maximum number of 7s in a number and the upper bound has 18 digits, then you can definitely find a number that has 15 7s, and then the last 3 digits are chosen so that it would be divisible by one of the coins and therefore definitely reachable. So the answer is at least 15, at most 18, and this gives you the possibility to brute force over all of the numbers that have almost all of the digits equal to 7, and this can also give you a valid solution. It's just somewhat nastier to implement for the 6 and 9s together case. And that's it.